Hello. A very warm good evening to all our participants. A few instructions before we start with our session. Uh, we would like all the participants uh, to post their questions related to the session in the chat box, which will be answered by our speaker at the end of the session. The feedback links will be shared in the chat box in Zoom as well as a YouTube live chat at the end of our session. We request all the participants to fill the feedback form with correct details based on which your e-certificates will be generated, and the certificates will be sent to your registered mail IDs within few days. And we'll be starting our session in few minutes.
Madam, can you hear me?
Yeah, I can hear you, sir. Good evening,
Yes.
sir. Can we start with the
Good.
session, sir?
Yes, yes.
Yeah.
Of course, yeah.
A very warm good evening to all our dear participants. On behalf of the Department of Chemistry, Bhaktavachalam Memorial College for Women, it's a moment of great privilege for us to extend a hearty welcome to all our participants who have joined us in the Zoom as well as YouTube live stream to this international webinar on cyclic and linear sweep voltammetry, fundamentals and applications. I'm really honored to welcome our Madam Principal, Dr. C.N. Ishwari, our Dean Madam, Professor S. Mangai, and all my dear colleagues who have joined us today. Established in 1993, our college is affiliated to University of Madras, and it gives me immense pleasure to inform that we have been imparting quality education since inception. The development of a quality educational system largely lies on the committed members of faculty, quality infrastructure, supportive administration, large pool of learning resources, and last but not the least, our hardworking students. I'm extremely privileged and honored to welcome and introduce our guest speaker, Dr. Anantaraj. He is a material and molecular electrochemist working on electroactivity of small molecules especially in energy and environmental science. Dr. Anantaraj has completed his bachelor's and master's from Presidency College, Chennai, and he has also cleared the SET and NET. He pursued his doctoral degree under the guidance of Dr. Subrata Kundu in Academy of Scientific and Innovation Research, SICRI, Karekuri. Dr. Anantaraj has been awarded postdoc fellowship by Japan Society for the Promotion of Science, and currently he is serving as JSPS postdoc fellow in Waseda University, Japan. He has also been awarded with S.K. Rangaraja Graduate Student Award in 2017 by Electrochemical Society, USA. Dr. Anantaraj has more than 56 scientific research publications to his credit, with more than 2,100 citations and an H index of 21. He is a reviewer of many reputed scientific journals like American Chemical Society, Royal Society of Chemistry, Elsevier, and many more. We are really happy to have such an eminent personality among us today. I may now hand over the session to Dr. Anantaraj. Sir?
Yeah.
Yeah.
Thank you very much for such a very nice introduction. Thank you very much for giving me this opportunity
Thank
to
you, sir. Thank you,
use
sir.
your esteemed organization as a platform to reach other researchers, colleagues, students, and faculty fraternity, and sharing my thoughts to them. So, shall I share my screen now?
Yes, sir, you can. Yes, sir, you can
Yes,
start.
yes,
Yeah, thank you,
yes.
sir. Yes, sir, you're on air.
Yes, 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 yes.
Yeah. Thank you.
Yeah, yes. Yeah, I got it. So I hope you can see my screen now. Yes,
Yes, sir, we can. We can.
yes, yes.
Yeah,
Yeah,
thank
thank
you,
you.
sir.
Uh, yeah, I again thank you once again, the BMC Chennai, for giving me this opportunity, because everyone needs a platform to show who they are. And as a young researcher, I also needed some push, and I'm really very thankful to the opportunity given by BMC. And I would like to share very few fundamental things about cyclic and linear sweep voltammetry, the fundamentals and application in today's talk, uh, which yeah, which I will start with the fundamentals. Uh, we all know that voltammetry is a versatile electroanalytical technique. In general, voltammetry includes everything: cyclic voltammetry, linear sweep voltammetry, chronometry, and so many other things. But in today's talk, I will be elaborating the basics of cyclic voltammetry and linear sweep voltammetry, and what are the things that we can do with these wonderful techniques. Actually, they are so versatile that you could do almost anything that you wish to do with the material you have or with the reaction that you want to study, whatever. It can be a versatile technique shading information on the reaction behavior of your material or the reaction that you wish to follow. So, in principle, in voltammetry, what we do is we are studying an interface by applying a predefined electric potential and measuring the response of the interface as electric current. So, in this definition, I have included these three words: interface, electric potential, and electric current. So let's first see what are they. What are they actually? Interfaces are nothing but junctions of two dissimilar uh, phases. Like they can be solid, 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 liquid, solid, gas, or liquid gas, or anything, or the combination of various combination of these three phases. So these are all called interfaces. In electrochemistry, what we do is we usually use an electrode or a combination of electrodes to study the nature of the electrode itself, or the reaction that undergoes on the surface of the electrode, or the reaction that takes place in the solution where the electrode is being inserted. So these are all basically constituting an interface. So I have included a few examples. Just a sec, I'll check. I'll change it to pointer. Yeah. So these are all few examples of interfaces. The first one represents solid-solid, the second one represents solid-liquid, and the third one represents solid gas. And final one where I have given represent solid-solid and solid-liquid interface. So these are all some common interfaces that we encounter in day-to-day electrochemistry things that we use in our life. So what we usually do in voltammetry is that we apply a potential on this interface, and we see how it behaves with applied potential in terms of electron transfer, which is measured by means of electric current. So we must know what is an electric potential first and what is an electric current also, in order to understand what we are looking for by doing this voltammetry. Electric potential is nothing but it is an amount of work done to transfer unit charge Q from one point to another point. The thing what I'm mentioning here as point is nothing but a phase which can be solid or liquid or anything else. So from one phase, one phase point to another phase point. In this case, the interfaces, that is what we are talking about. The one point is actually referring the electrode surface. The another point is the electroactive substance, that is the electrolyte, the reactive species in the solution. So for transferring a unit charge of a unit electric charge from electrode surface to the electroactive species, the amount of work we do is actually called electric potential. So which is measured in volts and usually represented with the symbol of E or U. So we use this electric potential as a thing that we give as an input to the system. So we measure electric current. So electric current is nothing but when we move charge from one point to another point by applying the which is nothing but electric potential. So we see the rate of flow of charge between the regions. Between the regions in the sense the point I said, from the electrode surface to the electroactive ions in the solution, or from the electroactive ions in the solution to the electrode surface. Between these 2 points, what is the rate of flow of charge is electric current, and which is expressed in amperes with the symbol of I, sometimes with J, which is called current density, which is usually normalized by the geometrical surface area of the electrode, and it is related to electric charge by this equation, which is nothing but the electric charge transferred per unit time. So this is what we are talking about: electric potential and electric current. So just by applying a potential, predefined potential, or in the case of linear sweep voltammetry and cyclic voltammetry, it is going to be a ramp of potential and a range of potential, which is basically called a potential window. So within this potential window, as we move the potential with time, what is happening to the system? When the system is start to respond in terms of current, and why it is so characteristic to the reaction that we are studying. What will happen if the concentration depletes at the electrode surface? These are all the things that we are going to see in the upcoming slides. So basically, what we are going to do is we are going to disturb the equilibrium at the interface just by applying a potential. So from that disturbance, from the perturbation that we imported, we are going to see how the interface react to the perturbation we made, which can give invaluable information about understanding the electrode surface and the reaction that the electroactive analyte, the electroactive anions or cations in the solution that it undergoes. So these are the things that we can get, and I will go into detail. So before going into the voltammetry in depth, so I want to make a few things explicit. We all know there are electrochemical cells. Electrochemical cells are basically two types. Actually, there is one more type which I don't want to include here. The main classification goes as the electrolytic and galvanic. In the case of electrolytic electrochemical cell, we have two electrodes which are basically cathodes and anodes, in which we apply an electric potential as an input energy, which performs splitting, or I can simply say which can enable the redox reaction, which provides sufficient energy to overcome the free energy required for a redox reaction to occur. So this is called electrolytic reaction. Examples of this cell include water electrolyzers, electrochemical sensors, whichever use the redox reactions of the analyte, which is to be sensed electrochemically, and the charging process of batteries. These are all examples of electrolytic cell, and this is the cell electrochemical cell that we use in voltammetric study. And another type is the galvanic cell, in which we are not applying any potential. We are getting electric potential and also electric current as a result of redox reaction that is occurring at the electrode surface, driven by thermodynamic potentials. Not we are not applying any electric potential from an external source and performing reaction. We are getting electric potential and current from a reaction which is thermodynamically driven and occurring on the electrode surface. So this is the basic difference between electrolytic cell and galvanic cell. So in voltammetry, the cell what we use here is electrolytic. Galvanic cell includes examples of all primary and secondary batteries that we are using in our day-to-day life, and discharging of Li ion batteries and other advanced batteries, whichever use the redox couples as storage mechanism. So these are the basic thing about electrochemical cells. So we also need to understand the difference between two electrode system and three electrode system, because this is two important thing in voltammetry technique. Because when we perform voltammetry just by taking a two electrode, in that case the counter electrode, which is referred as CE here, is also going to act as a quasi reference electrode, which means that the potential that we wish to apply on the working electrode to enable the redox reaction to go forward will also be depending on the potential which is experienced by the counter electrode, which means that the counter electrode's potential is to be the same throughout the reaction, but it cannot be, because when we perform an electrode oxidation or reduction reaction on a working electrode, this has to be equilibrated by the net ionic charge by performing a counter reaction on the counter electrode, which means that the counter electrode potential cannot be the same as it was before beginning the electrolysis process. So in two electrode system, whenever we measure a voltammetric response, it is the response of the whole cell, whole full cell. It is not the response of the working electrode or the material that you have coated or modified the working electrode with the material. So it is not the response of the single electrode. It is going to be the whole cell, the response of a whole cell, which is expressed in voltage, cell voltage, not as potential. So this is the main difference between two electrode and three electrode cells. And in voltammetric studies, what we usually intend to do is we are actually interested in studying a particular reaction, which can be oxidation or reduction or both, that is occurring on the working electrode. So the potential of the working electrode should remain the same throughout the reaction, which cannot be achieved with a simple two electrode system. So that's why the three electrode system is proposed. In three electrode system, what we do usually is we insert an auxiliary electrode, which is called reference electrode, which whose potential is not changing throughout the reaction, because it is actually a third half cell. I have given an elaborated image of reference electrode here. As you can see, it is actually a third half cell. So whenever you perform a voltammetric study using a three electrode system, you are actually using three half cells, working electrode and the solution inserted are constituting one half cell, and the counter electrode and the solution around it is constituting another half cell, and the reference electrode you use is the third half cell. In these two, the counter electrode and working electrode are in the same electrolyte solution technically, so they are performing the desired reaction on the working electrode and the counter reaction on the counter electrode. And meanwhile, the reference electrode, which is actually a third half cell, is not performing any reaction. So the potential of this electrode remains the same throughout the reaction, which means that instead of taking the potential on the counter electrode as a reference to control the potential on the working electrode, if we take the potential of the reference electrode as a reference to control the potential on the working electrode process and the potential associated with that process will not change with the reaction that is happening at the counter electrode, which means that whatever the response that you obtain with the three electrode system is purely of the response of the working electrode alone, not the whole cell. So this is the advantage of three electrode system. So in most of the cases, whenever we study a material for sensor application or water splitting application or whatever be the application, you name it, whatever it is. So when you want to study a particular material and you are coating it on a working electrode and you perform a 3 electrode system. So this is what we do in 3 electrode system. This basic difference must be understood in order to know what we are actually doing. So as I told, these are all the things that you should be aware before going into voltammetry in detail. So now I have told that there are two different cells and there are two different electrode systems that we use, and voltammetry is all about applying a potential, predefined potential or a ramp of potential, and measuring the response of the interface in terms of current. So we must know the current potential relationship before going into voltammetry in detail. So we have the very famous Butler-Warmer equation. All UG and PG students of chemistry study this equation and its derivation, and they all know one thing, that the current of an interface is varying linearly with over potential when the polarization range is very small within this region. I'm telling about this region because this is the region where the current varies linearly with the increasing potential, with the changing potential, I can say. So this is the region where the current varies linearly with over potential. And if you go higher over potential region, the current is no longer linearly varying. You can see an exponential relationship. So this is explaining that the current is always depending on the potential. So as long as you increase the potential, the current will also increase. Depending on the region where you are polarizing the potential, it could be having exponential relationship or linear relationship. But the major drawback of this equation, the Butler-Warmer equation, is that it has been driven assuming three things. One is that the oxidation and reduction reactions are happening at the same electrode, and second is that when these redox reactions are happening, there is no apparent change in concentration of the electroactive species at the electrode surface, which is actually not true in the practical cases. So this is the second assumption made. And the third assumption is that when you say potential in this, the over potential, when you say over potential, they assume that these over potential are free from IR drop. We all know that in all the DC circuit, every electrical circuit has its own intrinsic resistance. Wherever there is a resistance, there will always be a drop in potential between 2 points when you measure 2 points. So I'm telling about the electrode surface and the electroactive species in solution. So the potential which you apply on the electrode will not be the same which is experienced by the electroactive species in the solution because of this intrinsic resistance that is in the circuit. So there will always be a component of IR drop. So this Butler-Warmer equation is not considering these three facts. One is that it is saying that the oxidation reduction both are happening at the same electrode, which is not true, which cannot be practical. And the second thing is that the concentration there is no apparent concentration change according to this equation, which is also not true. And the third thing is that the over potential, what we discuss here is free from IR drop, which is also not true. So only from Butler-Warmer equation we cannot just correlate potential and current for all our voltammetry experiments that we are doing, because all our voltammetry experiments are to be done way far away from the equilibrium potential, where current potential relationship is exponential. So please be reminded of that one. The concentration is going to change when we perform redox reaction at a very high over potential. So it is important to now understand the relationship between cell potential and its dependence on concentration, which is given by another famous equation in electrochemistry. Everyone reads this. So the Nernst equation, which is actually derived from a very basic thermodynamics from which we know that for any reaction, the change in frequency is related by this equation. And we also know that the cell potential is nothing but the degrees in the free energy per coulomb. So which is related as this one. So taking these two relationship, we can get this equation where the Q is nothing but the reaction quotient, which means that the ratio between the reduced product and oxidized product in the case of reduction, and the equation takes this form, which is the very famous Nernst equation. So this equation is true for reaction which are electrochemically and chemically completely reversible and occurring via freely diffusing anions or cations, not the ions or electroactive species adsorbed on the surface. So this must be understood clearly. for a reaction, electrochemical reaction that we study, to be a Nernstian reaction, it should be completely reversible in terms of both chemical and electrochemical nature. So what we infer from this equation is that if the reaction is completely reversible and occurring via freely diffusing electroactive species, for any change in potential, there will be change in concentration, which will also lead to change in potential. So when the concentration of reduced species and the oxidized species are the same, the potential is said to be the half halfway potential, which is approximately equal to the standard electrode potential of the redox couple that we are examining. This is approximately equal. Please be reminded of that. This is approximately equal because this is not going to be the same value as that of the E of. There will be some difference because of the kinetic kinetic complexities associated with the redox reaction that we study. So if the reaction under study follows all these conditions, we can say these reactions are Nernstian reaction, and those reactions behaviors are said to be Nernstian. So we now know that the current potential relationship is exponential at very high over potential, and for a reversible reaction which is occurring via a freely diffusing electroactive species, they are going to be a change in concentration and potential always for any change in potential. So that will also result in change in current. So these are the things that we understand from voltammetry. So now let's move into linear sweep voltammetry. So in linear sweep voltammetry, what we do is we take an interface like this one, an electrode inserted in an electrolyte solution of anions and cations, and we apply a potential ramp, actually a potential ramp. So we begin from a potential called V1, and we slowly increase the potential with time and reach potential V2 with time say X. So this is what we actually do, but only from this relationship we cannot get any information about the interface. What we actually need is we need a figure or a graph such as this one, in which we have the potential, cell potential or cell voltage in the x-axis plotted against the current in the y-axis. So what we do is when we apply a potential ramp just like this to reach potential V2 from V1, we see change in current. At one point, the current start to increase and it keeps on increase and it attains a maximum, and then it again start to reduce, and then it attains a plateau. So when we reach V2, so this is what happening. So when we increase the potential by applying a ramp, we see increase in current, which is due to the reaction that is occurring on the electrode surface by the charge transfer between the electrode surface and the electroactive species in the solution. So this is what linear sweep voltammetry is all about basically. So just by applying a potential ramp with the suitable or the interested electroactive species in the solution, you can come to know two important things: where the oxidation is occurring, which is called the peak position, where it is starting, which is called the onset potential, and how much current it is delivering. So these are the important things that we get from linear sweep voltammetry. So this is usually used in studies and applications wherever the current density and potential over potential are important in order to qualify a catalyst or a material for energy application or sensing application or so on. So you name it. So this is the thing what we get from linear sweep voltammetry. So in cyclic voltammetry, we are just going to reverse the potential after reaching V2 back to the potential V1. So this is the fundamental difference between LSV and CV. In LSV, we just ramped up the potential from V1 to V2 and stayed there. In case of CV, we are reversing the potential again, remember, at the same rate to the starting potential V1. So in this case, what we do is we are getting the same response as to that of LSV we have just seen above, and when we reverse the potential, we are seeing another similar LSV, which is also increasing with lowering potential and attains a maximum and then start to decay, and then it also attains a plateau. So overall, we have a peak-shaped voltammogram. This is called a big peak-shaped voltammogram. In some people do also call this one duck-shaped voltammogram. You can actually see a duck here, right? It looks like Chuck in Angry Birds. So This is a typical cyclic voltammogram in a diffusion controlled reaction. So in the next slide, what we are going to see is why this peak-shaped voltammogram occurs. Why do we see? Why we see this peak-shaped voltammogram? This has to be explained based on the fact that when we apply a potential, we are actually starting a reaction, which means that the electroactive species. In this case, I have taken an example of the reduction of ferrocenium cation to ferrocin. So when we reach this potential, the reduction of ferrocenium cation begins, which means that the concentration at the electrode surface, the concentration of ferrocenium cations at the electrode surface start to decrease, and as there is more and more reduction of ferrocenium cation, we are witnessing increasing current density. So it reaches a maximum and then it start to reduce. So how do we explain this peak shaped voltammogram? In order to visualize that one, we need to understand this thing, the diffusion layer formation. This is a plot of concentration versus the diffusion layer thickness D, which means that the distance from the electrode surface to solution, the electroactive species, the concentration of electroactive species in the solution. So when we don't apply any potential at point A, this is at point A, the concentration of the green line, which indicates the concentration of reduced ferrocene, is 0, and the oxidized ferrocenium cation is almost full. It is equal to NT. So when we reach this potential, we are actually depleting the amount of ferrocenium cation at the surface. And when we reach point B, which is the halfway potential, where the concentration of ferrocin and ferrocenium cation are equal, we are actually having a situation such as this one, where at the electrode surface, the concentration of ferrocenium cation and reduced ferrocin are the same. We are having an equilibrium. That is why this potential is called E half, where the forward and backward the reactants that is involved in this equilibrium are the same. So what happens when we increase this potential further? When we increase the potential further, it starts to we start to witness the increase in concentration of reduced ferrocin and decreasing the concentration of ferrocenium cation. So clearly, so it attains a maximum at point C, because beyond which there is no more ferrocenium cations which can be further reduced to increase the current further. Instead, it has to depend. This electrode surface has to depend for the ferrocenium cation that has to diffuse from the solution to reach the surface electrode. That is why we are seeing a gradual decay in this area when we move from point C to point D. So you can see this is actually representing, this distance is actually representing the diffusion layer thickness. You can see when we increase the potential and reach point D, the thickness is increased largely. So at this point D, the concentration, surface concentration of ferrocenium cation is almost equal to 0. For any further current that you wish to see will be seen only when further ferrocenium cation diffuse from this area to the electrode surface. So this is the reason why we see a peak in a diffusion controlled reaction when you perform voltammetry in a static solution, which means that you are not stirring the solution, you are not doing performing voltammetry with a rotating electrode, or you are not sonicating the electrode solution. You are not doing anything. You are actually performing the voltammetry in static mode, in physical static mode. The mass transport is only due to the diffusion process that is happening because of the concentration gradient that is generated at the electrode surface as a result of the reaction that we led to happen by applying a potential trap. So this is the reason why we see a peak-shaped voltammogram. So what happened when we reverse the potential? The same is true. So now the surface is highly enriched with the reduced product, which is nothing but the ferrocene. So when you reverse the potential, we start to see the oxidation of ferrocene back to ferrocenium cation. So it increases as long as there is higher concentration of ferrocene, and it reaches an equilibrium just like as this one, point B, where we have reached point E. If you see the line connecting point B and point E, they are the same, which is called E half. We have again reached the point E half, which is nothing but the potential where the concentration of oxidized species and reduced species are again in equilibrium. So this potential is usually approximated for the redox potential, standard redox potential of the redox couple that we are studying, but which cannot be exactly equal due to various other reasons. Which one of such reason is that the kinetics, so which I will talk later. And when we move further from point E to F, we are again seeing a limitation, mass transfer limitation, where we have almost depleted the surface available ferrocene, and further current can only be witnessed when there is further diffusion from the bulk of the solution. So when we again reduce the potential to the starting point, and we can see the decreasing potential just like as the one we observed in this case. So this is the reason why we see a duck-shaped or a peak-shaped voltammogram when we perform CV or LSV in static condition. So what happens when we stir the solution or when we don't have a diffusion layer at all? So it is possible. These are all the cases where the electrode surface is sufficiently large, which are technically called macro electrodes. So the diffusion layer thickness is significant, which means that the diffusion has to occur through the diffusion layer, which is created as a result of concentration gradient that occurred because of the reaction that we effected by applying a potential ramp. But when we have a very small electrode with a very small area like an electrode with a diameter of few micrometer or few nanometer, so the diffusion layer thickness is going to be highly negligible, and the concentration gradient that is occurring on the surface of the microelectrode going to be very, very negligible. In that case, we will see a voltammogram such as this one. You will not see a peak-shaped voltammogram. You will not see a duck-shaped voltammogram. You will just see something like a sigmoidal curve with a hysteresis. Actually, there are so many things about this hysteresis and the separation between this potential separation between this hysteresis, which are very useful in electrokinetics analysis, which I'm not talking here. So if we get chance, we can in future. So this is a reason why we see a peak-shaped voltammogram when we perform voltammetry with a macro electrode in static condition when the reaction is diffusion control. So now we are going to see the effects of other factors. I said that we are ramping the potential, right? We are applying a ramp of potential in voltammetry basically. So what happens when you speed up the ramp, which means the ramp is nothing but the rate at which you apply a potential, which is technically called scan rate. So what happens when you increase the scan rate? So that's what we are seeing here. So in the first case, I said that we needed this much time to reach potential V2 from V1. So when we increase the scan rate, we are actually decreasing the time that is taken for reaching the potential V2, which means that the reaction will be affected in relatively smaller time. But the interesting thing can be seen here in this voltammetric response. As you can see that with increasing scan rate, the current density increases. This is one phenomena which also can be explained based on the diffusion layer formation. We all know that there is a famous law of diffusion proposed by Fick's, which is nothing but which relates the flux with the proportionality constant D to the concentration and the thickness of the diffusion layer. So which means that the concentration will be directly related to the flux, which will be increasing the current density. The thickness of the diffusion layer is inversely related to the flux, so which will be inversely related to the current density. So when we have very slow scan rate, we are actually letting the interface to grow the diffusion layer sufficiently large in thickness, which means that the diffusion layer becomes thicker when we apply a slow scan rate, which means that we are letting the system to create more concentration gradient by with a very low scan rate. So in that case, the diffusion layer thickness is very low, so that the flux of the electroactive species from the solution that is reaching the electrode surface is very low. As a result, the current density is also low. So when you increase the scan rate, you are not giving sufficient time to grow thicker diffusion layers. But the diffusion layer thickness becomes smaller and smaller as you increase the scan rate. So which means that the flux of the electroactive species that reaches the electrode surface is also increased, which means the concentration of electroactive species is increased on the surface. So when you perform more more oxidation reduction of electroactive species, which means that you are transferring more amount of charge. If you are transferring more amount of charge with the less time, which is nothing but increase in current. So that is why we see an increase in current when we increase scan rate. This is a peculiar characteristic of diffusion control reaction. Please be reminded that this is a peculiar characteristic for diffusion control reaction. So the reaction is kinetically controlled in this region, but not when it reaches a peak current. So beyond this region, it is diffusion control. So this diffusion control reaction is witnessing this increase in current density when we increase scan rate. So the same is true for CV. Interestingly, in CV we obtain other interesting things or characteristics about the reaction that is happening or the property of the electrode that is performing charge transfer. In this case, we have anodic peak and cathodic peak. The difference between these two peaks is actually called peak-to-peak separation, which is denoted by EP, and for a perfectly reversible reaction, which is in terms of both chemical and electrochemical reversibility, the peak-to-peak separation will be 59 millivolt divided by N. The N I have given is actually representing the number of electron transfer involved in this oxidation and reduction process. If it is 1, the peak-to-peak separation will be around 60 millivolt. So, which is a perfectly reversible diffusion controlled reaction. But in practical electrochemistry, it is very, very hard to achieve such 60 millivolt or closer to 60 millivolt. So when you have a modified electrode and if you believe that the reaction is completely reversible, you will always see peak to peak separation beyond this 59 millivolt. And researchers do agree that the reaction is reversible in the case when the peak to peak separation is as high as 70 or 75 millivolt, but with the one condition that the peak position is not shifting. So this should be kept in mind. So in CV, when we have diffusion control, when we increase scan rate, this is what happens. So the current density increases, but the peak to peak separation remains the same. And on the other case, if you take the the peak current ratio, anodic peak current ratio and cathodic peak current ratio, the ratio between anodic peak current and cathodic peak current, it will be exactly equal to 1. And the current will increase with the square root of the scan rate. This is very important, and this is defined by the very famous Randall-Sevcik equation, which actually help us to understand how peak current will increase with scan rate for a given analyte if it is undergoing a reversible diffusion control reaction with a freely diffusing ions. So in this case, we will be actually requiring the diffusion coefficient value and the absolute concentration in order to determine the peak current before performing voltammetry just from varying the scan rate theoretically. So this is what we see. So what happens if the reaction is reversible, but it is not occurring via freely diffusing anions? In most of the cases, when we insert an electrode to an electrolyte solution, the first thing that is happening in the interface is the accumulation of charges, because every electrode surface has its own work function, or I can say in other words, its own surface potential. So depending on the potential of the electrode that we insert or submerge into the electrolyte solution, there will be an arrangement of ions on the surface, electrode surface, which is going to be an electrical double layer, which is technically called an electrical double layer. So in the case of the reaction, the electroactive species could also undergo such adsorption on the electrode surface, and further electron transfer reaction when we apply a ramp of potential could happen via the adsorbed electroactive species. So here the reaction is still reversible both chemically and electrochemically, but not occurring via free diffusion. It is occurring via the ions, which are actually the species which we intend to study, adsorbed on the electrode surface. So in this case, the peak current and the scan rate are related by this equation. In this case, the scan rate is not related with the square root form. Here it is related directly. So the peak current increases directly with the scan rate. So just from these two equations, just by plotting these two equations, you can actually distinguish between the nature of reaction that is occurring. I mean, if you plot the peak current against square root of scan rate, and if it varies with linear linear relationship that is said to be occurring via freely diffusing ions. If it doesn't exert a linear relationship, try plotting peak current against scan rate, and if you see linear relationship between them, and you still have the peak to peak separation of 59 millivolt with increasing scan rate and the peak to peak IP-IC ratio 1, we can say that the reaction is completely reversible but occurring via adsorbed anions. So this is an example of wonder that you can do with a fundamental cyclic voltammogram, which many of us didn't or don't use in studies what we do. Yeah, this is one thing that we can do with CV. So basically, you can differentiate the reaction by the mechanism it occurs. So this is what we can do. So we are going to see now the reaction rate and its effect on CV and LSV. I have told that if the reaction rate is faster than scan rate, the speed at which we ramp up the potential, there is no issue with the peak current and peak potential, because they will be occurring faster than the time of the scan rate, the speed of the scan rate that we apply. So in the case when the reaction rate is lower than the scan rate we use, we usually see such difference or shift in the potential. So this is what we see. And the same is true in the case of cyclic voltammetry also. So this happens when the rate constant varies. So this can be used in studies wherever if you are interested in studying the chemical reactivity of a molecule in presence of a catalyst or in presence of a poisoning agent, you can just take a compound that you are interested in studying. You can perform CV or LSV without adding the poisoning agent or catalyst, and again you can add the catalyst or poisoning agent, and you can see if the reaction without catalyst is having higher potential. If you add a catalyst, the potential will be reduced to the lower region. If the poisoning effect is there, the potential will be shifted to the higher over potential or over voltage region. So just by performing the cyclic voltammetry with the desired poisoning agent or catalyst, you can actually study the rate of the reaction. This is another thing that you can do with voltammetry. So now we are going to see another type of reaction which is called quasi-reversible reaction, which is reversible but not kinetically so facile. That is why these reactions are called quasi-reversible reaction. And these reactions characteristics include peculiar characteristics, which is nothing but the peak-to-peak separation. So the peak-to-peak separation is always larger than 59 millivolt. From this, you can simply say the reaction is quasi-reversible. So if you can see, even at the very low scan rate, the peak-to-peak separation is as large as 150 millivolt. So this is very large when compared to this one. So we can say this kind of reactions are quasi-reversible reaction. So their anodic and cathodic peak current will not be the ratio of anodic and cathodic peak current will not be equal to 1, and the peak position is always be shifting to the higher over voltage region with increasing scan rate. So this is what happens when you have a quasi-reversible reaction. So just by performing CV or LSV with increasing scan rate, you can actually say whether your reaction is reversible, occurring via freely diffusing ion, or occurring via adsorbed ion, or it is quasi-reversible. So it is how we infer or interpret the voltammetry data. So now we have another type of reaction, which is an irreversible reaction. As you can see here, this is a typical CV. When you apply a reduction potential, the electroactive species is being reduced. But when you come back, you are not actually witnessing a oxidation potential or a very low oxidation potential. This indicates that the product which is formed as a result of reduction is too hard for oxidation, or it is too stable chemically so that we are unable to oxidize it, or it is escaping from the solution, electrolyte solution. So this happens only when these two possibilities are there. So this can be identified just by increasing the scan rate. When you increase the scan rate, the reduction current will also increase, but in the case of the backward sweep, you will not see any oxidation peak. So this is a peculiar characteristic of an irreversible reaction, which is controlled by diffusion. So just by performing CV, you can actually come to know these many things about your electroactive species and your solution and your electrode surface. So this is how voltammetry can be used in a versatile manner. So now we are going to talk about effect of IR drop on reversible reaction, which is controlled by diffusion. We know what is IR drop because I have told that every electric circuit, DC or AC, every electric circuit has its own intrinsic resistance, which cause a drop in potential between 2 points. The 2 points, we reminded that the 2 points I'm talking here is always about the electrode surface and the electroactive species in the solution. So as a result, what happens is when you increase the potential, even though the reaction is reversible and completely reversible in terms of both chemical and electrochemical nature, you will see a shift in potential towards the higher over voltage or over potential region with increasing scan rate. This is quite confusing, right? The scan rate effect and quasi-reversible reaction, which I have showed here, is also the same as this one. So it could be sometimes problematic. We may not be sure whether the reaction is actually reversible or showing this phenomena because of IR drop, or my reaction is actually quasi-reversible. So in order to know this one, you can do one thing. One thing is performing IR drop compensation manually. When you do that one, at least at the lower scan rate, as you can see, the lower scan rates, the peak potential remains the same, which means that but just by performing IR drop potential, you can actually overcome the effect of IR drop. So your reaction can be said to be reversible. But we also have to be very careful that this reaction can also be quasi-reversible in nature, and we are by performing IR drop compensation, we may be reversible reaction. So how can we distinguish quasi-reversible reaction and IR drop affected reversible reaction? Here comes the solution. So this is what we can do. We know the concept of supporting electrolyte, and I told that the IR drop is mainly because of the intrinsic resistance that is existing in the circuit. And the main component that constitute to the overall uncompensated resistance is the solution resistance, which occurs from the resistance of the electrolyte solution we use. So how can we minimize the solution resistance of the electrolyte? One way is that increasing the supporting electrolyte concentration. I believe that you people know the concept of supporting electrolyte. The supporting electrolyte is nothing but a pair of ion, which is actually formed from a salt, which is totally redox inactive. They do not undergo any sort of charge transfer reaction on the electrode surface within the studied potential window. These electrolytes are called supporting electrolytes, which are used only for the reason of improving the conductivity in the solution, so that we are minimizing the solution resistance. So this is what we are doing. So if you want to find out whether the observed behavior, the increasing scan rate shifting the peak current, peak position, is actually due to the quasi-reversible nature or because of IR drop compensation, I would suggest you to go with this experiment. You perform an experiment with low amount of supporting electrolyte and perform IR drop compensation. You will see change in peak feature. And when you perform the same CV with a very high concentration of supporting electrolyte, which means that you are lowering the solution resistance, you can see at lower scan rate, the peak position remains the same. So in this case, this reaction is actually reversible, but we see peak shift with increasing scan rate because of ohmic drop, the IR drop, the solution resistance. So this is how you can distinguish between the actual quasi-reversible reaction and the reversible reaction that is affected by IR drop. So this is one example how voltammetry can be effectively used in order to distinguish between the type of reaction. So now we are, I have so far been discussing about the reactions that we can study with CV and LSV, which are reversible and quasi-reversible, and mainly diffusion control. Now we are going to see some examples of kinetically controlled and totally irreversible reaction. So this is an example, oxygen evolution reaction catalyzed by NaFeLDH and stainless steel scrubber, the hydrogen evolution reaction and the oxygen evolution reaction on the other hand. So in this case, what happened is that in this case, the product which is formed here is nothing but the oxygen gas and the product that is formed here is nothing but the hydrogen gas. Once the product is formed, that is escaping out of the solution from the electrode surface, which means that there is no practical concentration gradient occurring, which means that there is no diffusion layer formation. When there is no diffusion layer formation, the current will be totally controlled by the concentration of the electroactive species on the electrode surface, which is not changing practically. So as long as you increase the potential, you will be witnessing increasing in current density. You will never see a limitation, a peak, or a decrease in peak. So this is the basic difference between kinetically controlled irreversible reaction and the reversible diffusion controlled reaction. So this is what happens when we have a kinetically controlled irreversible reaction. The examples are water electrolysis, as I have shown here. Other molecules which produce gases. Example include hydrolysis of electrolysis of hydrogen and electrolysis of ammonia. These molecules also produce a gaseous product, and the anode, which is nothing but the nitrogen gas. In that case, we will be seeing a similar voltammogram with no peak. So you will be witnessing increasing current as long as you increase the potential, which will be exponentially related to one another, as per the Voltammetry equation, of course. So now we are going to see the effect of scan rate and analyte concentration on an irreversible kinetically controlled reaction. I told that scan rate can severely affect the current, peak current that we see in diffusion controlled reaction, and concentration is directly proportional to the current what we see in diffusion controlled reaction, right? In the case of irreversible kinetically controlled reaction, here I have shown an example of copper hydroxide, copper oxide grown on copper foil for methanol oxidation. So this is for methanol oxidation in KOH. So in this case, I have increased the scan rate, that is the speed of the potential ramp that I have applied in this potential window from 10 millivolt to 200 millivolt as 10, 50, 100, 150 and 200 millivolt. You can see there is no increase in current density. So this is a peculiar characteristic of a completely irreversible kinetically controlled reaction. So this is what happens when you have a completely irreversible kinetically controlled reaction, and this can be witnessed with all cases of gas evolution reaction. That can be oxygen evolution, hydrogen evolution, or nitrogen that is evolved from ammonia oxidation or hydrogen oxidation or urea oxidation. So this could be anything, any gas evolution reaction. This will be the response when you increase the scan rate, which means that the kinetic current is independent of scan rate. Okay, so one interesting thing that you can notice here is that this is the self oxidation and reduction peak of copper hydroxide to copper oxide hydroxide and copper oxide to copper oxide hydroxide, which is controlled by diffusion. That's why we witness increase in current density with increasing scan rate. So with a single figure, you can actually witness two different reactions: a diffusion controlled self oxidation of the catalyst material, a kinetically controlled oxidation of methanol. So that's how scan rate affects the diffusion control process, and that's how it doesn't affect a kinetically controlled process. So what happens when you increase the concentration of electroactive species? In the case of irreversible kinetically controlled reaction, the case is going to be the same as that of diffusion control process. In the case of diffusion control process, I said that increasing concentration of the electroactive species, where I explained about lowering the diffusion layer thickness just by increasing the scan rate, where we are actually increasing the amount of flux, which means that increasing the amount of electroactive species on the electrode surface. So there we have witnessed increase in current density, and same is true in this case also. So even for electrochemical irreversible gas evolution reaction such as this one, when you increase the concentration, the current density will increase. So this is something we can differentiate just by varying the scan rate and concentration using a simple cyclic voltammetry. So now I have shown some fundamental things and the characteristics of reversible, quasi-reversible, and kinetically controlled irreversible reaction with respect to scan rate, diffusion, and the concentration. Now we will see what are the possible applications of this voltammetric techniques. The very first application people use in all sort of electrolytic reaction that is being monitored using voltammetry is that to determine the potential at a desired current density, of course, or the onset potential. So this is one of the major application of voltammetry. Here I have shown an example of water oxidation for a set of given catalyst and for a current density of 10 milliampere, the over potential values. Actually, these are reflecting uh, the catalytic property of the electrode used for the oxidation of water. So linear sweep voltammogram as well as the cyclic voltammogram can be used to determine the over potential required by a particular electrode for a desired process. This is one of many applications that we can use these voltammetric techniques. And the second one is the electrochemically accessible sites determination. In most of the cases when we perform electrocatalytic reaction, turnover frequency calculation is a very important parameter because that is a measure saying how faster is your catalyst in performing this reaction, for which you need the exact amount of catalytic sites that is participating in your desired electrocatalytic reaction, which can be calculated just from the self oxidation and or reduction peak of the catalyst from the CV or LSV that you recorded. In this case, what you are going to do is you just integrate the area under this peak, and you know the scan rate, and divide the charge with the scan rate. You will get you just divide the area by the scan rate. You will get the charge in coulombs, which can be divided by the charge of an electron, which can be uh, showing the number of electron transfer for this oxidation. And if you know the number of electron transfer process of this particular oxidation, it is a single, whether it is a single electron transfer process or double electron transfer process, you can actually come to know the number of involved catalytic sites. So which can be used for the determination of TOF. So this is another application of voltammetry, and we can perform electrochemical surface area determination by CV in non-Faradaic region, performing in non-Faradaic region. So let me first clarify the difference between Faradaic and non-Faradaic. In the case of Faradaic region, we have seen the peak-shaped voltammogram, whatever I have explained and showed you in previous slides. In this case, this is just going to be the current that we see as a response of increasing or ramping up the potential or cycling the potential, that is resulting only from the adsorption and desorption of the ions on the electrode surface. So which will be helpful in determining the double layer capacitance, because by doing adsorption and desorption, we are actually making an electrical double layer, and the double layer's capacitance can be determined from this CV, and the related EXA can also be determined from this CV. This can be used to monitor change in electrochemical surface area before and after certain electrochemical operation, or can be used to compare two different set of electrocatalysts for a same reaction at the same electrochemical condition. So this can be done with voltammetry. And one more important application of voltammetry is that some lazy people like me use voltammetry and voltammograms that were obtained with a very slow scan rate to derive Tafel plots. When I have explained about the Butler-Walmer relationship, the current potential relationship, I told that the current varies exponentially with the high in the high over potential region, which means that if you plot the exponentially varying current as logarithmic current against the over potential, which is free from IR drop, you will be having a linear line, the slope of which is equal to the constants in the Tafel equation, which will be something like between 30 to 120 millivolt per decade, depending on which you can also predict the number of electron transfer that is occurring on the rate determining step, and also the mechanism by which the reaction is occurring. So this is a very important application of voltammetry, which can be used to derive Tafel plots. But be reminded that this is not the ideal approach for deriving Tafel plot, because Tafel plots are said to be actually they are called in other terms steady state polarization curve. But the response what we use here from voltammetry are not obtained at steady state. They are actually obtained by ramping the potential, which are actually not representing steady state. So this difference can be causing some false measurement in the actual data, particularly when we are interested in calculating the exchange current density of the electrode under study. So this is shown by Fabry et al. In an important report 2014, where they studied the difference between the Tafel lines between the one obtained with chronometry and the one obtained with the cyclic voltammetry at 5 millivolt per second. In the linear region where we measure Tafel slope, there is no apparent difference. But as you can see, the exchange current density, which will be obtained by extrapolating this linear region, can be highly different from one another. So there is a big difference. So you cannot rely on the Tafel plot that you obtain by replotting the voltammetry that is occurred with a very low scan rate for calculating, for accurately calculating exchange current density. So I would suggest you to go for chronoperimetry or chronopotentiometry, the steady state techniques, or of course the electrochemical impedance spectroscopy. And apart from that, we can also study the surface characteristic of a given electrode material. If you have an electrode material and if you don't know the surface composition, I have shown an example of copper foil here. I have chosen a very large potential window, as you can see, minus 1.5 to 1. Within this, there are several peaks that you can see, and in the backwards scan, you can also see several peaks. All these peaks can be assigned to the respective redox reaction that is occurring, as I have assigned with the help of standard electrode potential table that we already have in literature. So cyclic voltammetry can be used to study the surface of the material that you wish to study. In the case of alloys, suppose if you have copper nickel alloy or nickel iron alloy, copper, nickel, iron, they all have their own characteristic oxidation and reduction potential for formation of oxides, hydroxide, oxyhydroxides, or tetrahydroxy anions, or the reduction of tetrahydroxy anions. So from such a CV of an alloy, you can actually show a semi-quantitative surface composition between two different elements in your alloy material. So this is another application that you can do with cyclic voltammetry. So this is the diffusion coefficient, which is very important when we are interested in promoting a particular redox reaction for industrial level production of a particular product or something. The diffusion coefficient of a solution must be known. Other than that, for studying the reaction kinetics, the diffusion coefficient is also important. I told that when the reaction is diffusion controlled and completely reversible and occurring via freely diffusing electroarc species, we can obtain a linear plot by plotting the peak current against the square root of scan rate, such as the one I have given here. You can see a linear relationship, the slope of which is equal to this one. Just by rearranging this equation, you can get diffusion coefficients. So for each oxidized product as well as for reduced product. So once you have decided, you have determined the diffusion coefficient, you can also use this diffusion coefficient to calculate the concentration of the same species in an unknown solution, just by using the CVs that were obtained with different scan rate. So this is one of the applications. This can be used in environmental monitoring, pollution control, and treating hazardous material like hexavalent chromium in a very low amount, because cyclic voltammetry is a powerful technique capable of detecting pollutants in the concentration as low as picomolar quantity. So when you have performed this experiment, and if the reaction is completely reversible with occurring via freely diffusing electroactive species, just by determining diffusion coefficient, you can use this particular equation to calculate the concentration of the same species in an unknown solution, so that it can be used for various applications, including sensor, pollution control, and monitoring a particular toxic species in a reaction mixture. So many other things you can do. So the final part of the application section, studying the reaction mechanism using CV. So this is a very interesting thing. This is one of the thing that I admire most about the cyclic voltammetric technique. So we can actually study the mechanism by which the electrocatalytic reaction is occurring. So here I have given a example of EC mechanism, where the E stands for the reaction that is occurring on the electrode, and C stands for the reaction that is occurring via the reduced product that is forming another product chemically. So this is chemical process, this is electrochemical process. So what happens is, when you reduce O supplying an electron, it forms R. When you reach this potential, so there is no O further for further reduction. But when you reverse the potential, you are not seeing the oxidation of R. because R is already converted into some other product which is not oxidizable. So just by performing CV, you can say this thing. So the reaction is actually occurring via a coupled chemical reaction. So this is what you can do. So this you can actually confirm by just varying the scan rate. In the case of higher scan rate, sufficiently higher scan rate, when you don't have sufficient time uh, when you don't have sufficient time for the product to reduced product to form further chemical products, you will actually see the oxidation peak. But when you perform the reaction at very slow scan rate, you are actually letting the reduced product to get converted into the desired products through chemical reaction, so that you are not seeing any oxidation peak. So just by varying the reaction scan rate, electrochemical reaction scan rate, you can actually confirm whether the reaction is mechanism is following EC mechanism or not. So in the case of increasing kinetics, I told about the rate of the reaction could affect the peak position. The same is true. So just by adding a catalyst or some other thing, you can witness a change in peak position. If the catalyst is enhancing the activity, you will see lowering in peak potential. If the catalyst is poisoning the activity, you will see increase in potential. The scan rate dependency is going to be the same in the case of changing rate also. So this is how CV can be used to define mechanism. And I have shown another example of ECE mechanism, in which the reduced product which gets converted into ACE chemically undergoes further reduction to form T. So there is actually two reduction reaction which is happening via a chemical process. In this case, we will have a CV such as this one or such as this one, depending on the reduction potential of the chemically formed S. If the reduction potential of chemically formed S is higher than the reduction potential of O, you will see something like this, because it requires more potential to reduce. Then you will see like this. But the formed product, because of the reduction of S, is not undergoing any sort of further chemical or electrochemical conversion. So it will be oxidized back to S when you shift back the potential. But when you come here, you don't have any S, any R. So that's why you are not seeing any oxidation current in this case. So when you have a CV like this, you can simply say the reaction is happening via ECE mechanism, in which the chemically formed product is harder to reduce than the starting material. There is another example when the starting material reduction potential is higher than the reduction potential of the intermediate product, which is formed via chemical reaction. In this case, you will see something like this. In the first sweep, which is in the black color, you will not see any further reduction peaks, because the formed S, which is also getting reduced along with the O. That's why we are seeing higher current, relatively higher current. When you come back, the T, which is formed by the reduction of S here, is oxidizing. When you go back here, this in this place, you are again seeing the oxidation of S, which is formed as a result of which is having lower reduction potential than the starting material. So these are the difference between the ECE mechanism when you have higher reduction potential for the chemically formed product, when you have lower reduction potential for the chemically formed product. Otherwise, another type of reaction is also possible, which is given here, which I don't want to explain. You can simply correlate just as I explained here. And finally, we have EC prime mechanism, which indicates the catalytic reaction, which is nothing but the formed reduced product in presence of a catalyst undergo a reaction which actually generates the starting material. This is kind of interesting. So when you reduce the product, it forms R. R in the presence of Y start to again regenerate O. So in this case, in the first cycle, you will be actually seeing with a low concentration of Y, the catalyst, you will be actually seeing some oxidation current of R, because there is sufficient R, because there is no catalyst to convert this R into O. That's why you are seeing oxidation current in the backward shift. But when you have sufficiently high catalyst amount, which is involving in the conversion of R back to O, you are seeing only the oxidation current, only the reduction current, not the oxidation current. So if you are experiencing such a behavior in your CV, when you increase the scan rate, you can, when you increase the catalyst amount, you can blindfoldedly say that the mechanism is following electrochemical and catalytic mechanism. So this is how a simple CV, cyclic voltammetry with increasing scan rate, can be used to study the mechanism by which the electrochemical reaction is happening in your solution. So there are so many other things that I have not covered here, which includes sensors, capacitors, and whatever, electrolyzers, whatever you name it. So these things are there are so many other things that you can do with this versatile and powerful voltammetric technique. I just want to summarize the things that I have shared with you. So basically, in voltammetry, we study the current response of an interface by applying a ramp of potential. So that's what you want to know. And most reactions that we practically see in lab are quasi-reversible or irreversible in nature. So you can distinguish just by varying the scan rate, as I have explained. So voltammetry can be used to determine over potential, electrochemical surface area, number of ions participating, electrochemically accessible number of sites in the electrode, and redox feature of any compound that you wish to study, the capacitance of an electrode material, or the type of reaction that it undergoes, and diffusion coefficient, concentration if the diffusion coefficient is determined, and finally the mechanism. And of course, you can do capacitance, capacitor studies, studies related to batteries, studies related to corrosion prevention, studies related to electrochemical sensor, whatever. You can do so many things with this voltammetric techniques. But what I see is that I received so many papers for peer review from various journals. We all know that the revolution caused by nanoscience and nanotechnology and the evolution of material science has triggered almost 90% of the global researcher population to work on interdisciplinary fields, so that people, what usually do is that they create some material that can be a catalyst or a support material or something else, or an anode material for a battery application, or cathode material for a supercapacitor application, whatever. So what they do is they perform some CV in a desired solution and they report it as it is. But they don't know many basics, and they do actually lack in basic knowledge. So I urge you all, if you are an interdisciplinary researcher and working on applied electrochemistry, please read the basics, and you will be like Captain Rogers. You will become worthy. I'm not saying that you are unworthy now. You are already a superhero, because in my view, all researchers are superheroes, just like Stephen Rogers. But you would become more worthy when you know the basics and do wonders. So that's what I wanted to study. Sorry, that's what I wanted to share with you. And yes, we work on electroactivation of small molecules, just as Dr. Sangeeta introduced in the introduction. And we also do some fundamental electrochemistry. And we are open for collaboration. If you are interested in working with us on electrochemistry, if you have some interesting material that you think it can be used for electrocatalyst application for electroactivation of small molecules, and if you have some interesting compounds that can be organic, inorganic, or organometallic, and you wish to study the electrochemical property such as the diffusion coefficient and the redox reaction that it undergoes, you can write to us, and we are happy to help you, and we can have some fruitful collaboration. And I should acknowledge the funding agency which support my research works. Firstly, from January 2019 to present, the Japan Society for the Promotion of Science through the JSPS postdoctoral fellowship, and from 2014 to October 2018, CSIR India via junior and senior research fellowship. And I also wish to thank my lab members, senior researcher, and Professor Noda, who are there for helping me in all my needs. And I must not forget to thank my earlier group members, and particularly my mentor, Dr. Suprada Kundu, who taught me a lot. And I also must thank all my advanced electrochemistry tutors who taught me all these things. Yeah, thank you very much.
Thank you very much, sir.
Yes.
We have been receiving excellent feedback throughout the session.
Okay, that's nice to hear.
Really very happy on that, sir. There is a saying that there are two ways of spreading light, to be the either to be the candle or the mirror that reflects it. So we are really happy to say that you have lightened and expanded our knowledge on the topic to a greater height, sir. Thank you. Thanks a lot.
Thank you.
So we have few questions which has been raised by our Zoom participants as well as the YouTube live streaming participants. So shall I
Yes,
just share that slide, sir, for you to answer?
yes, yes,
Yeah, yeah, sure,
yes,
sir.
sure.
Can you just view my slide, sir?
Yes, yes, I can see, I can see.
Yeah,
Yeah,
yeah, yeah.
yeah, I'll read. Yeah,
Yeah, yeah. So we have around 13 questions, sir.
yeah, no problem, no problem.
Yeah,
Yeah, I'll answer one by one.
yeah, yeah.
I have time, no issue.
Sure.
So yeah, now full MC, how can we decide the exact potential window for CV and LSV? Yeah, that depends on two things. One is the stability of your electrode material and the stability of your electrode solution. If you are using aqua solution, you should always restrict your potential window within 1 volt, because beyond 1 volt you will be splitting water actually, and that can happen even with lower potential if the electrode material is highly active, catalytically active for splitting water. So it actually depends on two things. One is that the electrochemical stability of your electrolyte, and the second thing is that nature of electrode material that you use. And Anil Gite, can we determine the thickness of the diffusion layer at any instant? I think we can. Yes, I think we can, because we see difference in current density with increasing scan rate, which means that we know the time, and we also see the difference in current. So if you determine the diffusion coefficient, you can actually determine the flux that is transferring from the bulk of the solution, which is actually will be shedding light on the thickness of the diffusion layer. And Balamurugan, what kind of material or element in the working electrode? Any noble gas burst in the cell? So, that depends on the type of reaction that you are studying. If you are interested in studying oxygen reduction reaction, for example, all aqueous electrolyte generally has some dissolved oxygen. In that case, it can have a background noise or background contribution from the reduction of dissolved oxygen too. In that case, you may have to purge noble gases like argon or some inert gases like N2. So in other cases, you don't have to do all these things. And Vignesh, why we are using ferricyanide solution for GC optimization process? Is it possible to reduce? It is possible to reduction of CO2 by using 3 electrode system? If yes, please explain me, sir. Yes, ferricyanide and ferrocyanide are they are the they are the redox couple, which is very famous for studying the electrodes and charge sensor process, because they are highly reversible and diffusion controlled when you perform with the macro electrode, and they are occurring via freely diffusing uh, ions. So the very first case I have discussed, which means that the peak to peak separation will always be closer to 60 millivolt, and anodic and cathodic peak current ratio will be equal to 1, and the scan rate, the peak current will be linearly varying with the square root of scan rate. So this is how you characterize your glassy carbon electrode. So this is how you come to know whether you have perfectly polished your GC carbon electrode or not. So that is why you use it. Yes, of course, you can perform CO2 reduction in a 3 electrode system. So many people do this one just to determine the electrocatalytic activity of your material. But when you perform CO2 electrolysis in full cell, you must always have to couple this reaction with the OER or chlorine evolution reaction, or in fact, you can also perform other less energy consuming oxidation reaction in addition to CO2 reduction at your cathode. And Rosalind Vimala, how to identify number of electron transfer in complexation from its CV. Yeah, if you can see a redox peak in your CV for the complexation reaction, it's very simple. And if you also know the number of electron transfer involved in the complexation reaction. For example, if the complexation reaction is actually involving in the transfer of one electron, you can simply divide the charge of an electron with the overall charge that you get by integrating the area under the redox peak. If it is the 2 electron process, the complexation reaction is 2 electron reaction, you have to divide by 2. So this is how you get the number of electron transfer involved in the reaction. So Jocelyn, what is the exact role of reference electrode in 3 electrode system, and will it affect if we use two electrode system for the same sample, what does the potential versus AgHCl really means? A very good question. I actually wish to uh, explain this one when I was explaining two electrode and electrode system. Actually, the reference electrode is mainly because when you have only two electrode in a solution, in the very first position, when you don't apply any potential, the potential on the working electrode and the potential on the counter electrode, they are all actually measured by the difference between the potential of these two. So when you start applying a potential on your working electrode, you are actually polarizing the working electrode with reference to the potential of the counter electrode, right? There is no issue unless there is a reaction, electrochemical reaction on the working electrode. Once you are starting to witness a reaction on the working electrode, a counter reaction must also occur on the counter electrode, which will vary the potential on the counter electrode, which means that the potential which now you are experiencing at the counter electrode is not the same as the one you have had in the beginning of the reaction. So the potential at the counter electrode will also be affecting the potential on the working electrode. That is why we introduced a third electrode, which is actually not polarizable, which is actually not polarized throughout reaction, and the potential is remaining the same throughout the potential ramp, and the same potential of the reference electrode is used to monitor or control the potential that is being applied on the working electrode, which means that the working electrode potential is now freed from the effect of counter electrode. So that is the reason why we use reference electrode. When we see potential versus AgHCl means it is which means that the potential is obtained with reference to AgHCl electrode. So which has standard redox potential of this for this redox pair you have standard redox potential of 197 millivolt. If the KCl solution you have in your AgHCl electrode is 1 molar, if it is 0.1 molar, it will be even higher. So depending on the concentration of the electrolyte you have in this reference electrode component, so you will be having different standard electrode potential for the reference electrode. Be sure that you are using the same concentration of electrode in both the cell as well as in the reference component, because when you have two different concentration of the same, even though the same electrolyte, for example, you are performing voltammetry measurement in 1 molar KCl and you are using AgHCl electrode with a electrolyte solution filled with 0.1 molar KCl, you are actually having two different concentration at the junction of the porous interface what we have between the cell electrolyte in the cell and the reference electrode compartment. You are actually having a concentration gradient, which will also lead to the formation of something called a kind of liquid junction potential, which will add up to the reference electrode potential. So there we will be obtaining false measurement. So in reference, when you use reference electrode, be sure to use the same electrolyte with the same concentration in both cell as well as in the reference electrode compartment. Yeah, I guess I made it clear. Thank you. And Shamim Abdul Samad, what is the difference between reversible and quasi-reversible, whether the diffusion control or not? Irrespective of reversible or quasi-reversible reaction, the diffusion control is determined by the nature of the reaction. In the case when the reduced or oxidized product stays at the surface of the reaction, it will create a concentration gradient and it will also cause a growing thickness of the diffusion layer, which means that the further electroactive species has to diffuse through the layer of formed product, which means the reaction will be controlled by diffusion. It is irrespective of the nature of reaction, whether it is reversible or quasi-reversible. The reaction can be diffusion controlled when you have the products in the solution even after the reduction or oxidation. And Sedupati, how to calculate the electron transfer from CV? It is very simple. You can just give me a mail. I have done this thing in so many my works, and I will share you the details in email. I will simply put in this way: we have current against potential against current, right? When you take area under a peak or oxidation peak or a reduction peak, it is actually going to be I actually amperes. When you divide this area by scan rate, it will be giving the area in ampere second. Ampere second is nothing but your charge, which is expressed in coulombs. So now you know the charge associated with the peak, and you also know the charge of an electron. When you divide the charge you calculated from the CV by the charge of an electron, you are actually calculating the number of electron transferred in the reaction. So when you know the actual number of electron transfer associated with the reaction, you can have that number of electron transfer you determine and you can use that to relate to the number of electrochemically active or accessible sites. So, Sandhya Jayachandran, how does a non-ferrodic material behave when CV is taken? Is the CV different for ferrodic and non-ferrodic material? Yes, absolutely they are different. The term ferrodic and non-ferrodic means that when you have a ferrodic reaction means you are actually transferring electron across the interface from the electrode to electroactive species or from the electroactive species to the electrode. When you have ferrodic, non-ferrodic mechanism or non-ferrodic current, you are not actually affecting any electron transfer. You are just uh, actually affecting adsorption and desorption of electroactive species in the solution. And the current, whatever you see, is going to be uh, actually very minimal, and the increase with respect to current rate will be similar to that of reversible and quasi-reversible reaction. In the case of non-ferrodic current, you will not be seeing any peak in your CV. In the case of ferrodic current, you will be seeing clear oxidation and reduction peak. And Dr. D. Ramesh, is it possible to analyze the antioxidants using CV technique? There are so many antioxidants. I guess antioxidants are the material that oxidize themselves to prevent the oxidation, right? So if your antioxidant have a specific reaction, and if you know the associated redox potential, you can select a suitable solvent, and you can put the antioxidant in the solution and put a set of electrodes that can be inert towards the surface changes like PT or gold, and you can perform CV. Of course, you can study your antioxidants with CV. And if you need some help, you can write to me. You are most welcome to write, and I'll be happy to help you. And Dr. Sobana, how should we apply CV in photocatalysis? What details that it infer in photocatalysis reaction? Is it possible to water soluble compounds? I don't know about photocatalysis, but I have a few experiences in photoelectrocatalysis, where we do is where we combine photocatalysis and electrocatalysis together. What we do there is we actually apply a ramp of potential, and the same time we will also irradiate with the artificial solar simulator the catalyst under study. So we see the combination of effects of both uh, photon that is used to excite and the applied potential. So that's what we do. And I'm sorry that I don't know about photocatalysis. Sorry. And Gopi Ruth, can we calculate the order of reaction from CV? Of course we can. Of course we can calculate if it is completely reversible and occurring via freely diffusing species. And there are examples of calculating reaction rate, which is actually useful in calculating the order of reaction. And Dr. N. Senthil Kumar, can we identify the fuel cell anodic oxidation mechanism with the aid of CV studies? Yes, of course we can. I assume that the fuel cell you are talking about is hydrogen oxygen fuel cell, in which the anodic reaction is hydrogen oxidation reaction, which is a very well studied reaction in cyclic voltammetry, using cyclic voltammetry and CV, which is a diffusion control reaction. And depending on the material, it can be peak shaped, triple peak shaped, or can come with shoulders, depending on the phase of PT that you use for oxidizing this hydrogen. In the case of, I guess, yes, you can do whatever the fuel is that you are oxidizing at the anode, you can study its performance using CV. Yes. Thank you. Yes.
So there is
Thank you, madam.
a yeah, thank you, sir. There's one more question from YouTube live chat. Sorry.
Okay. Okay. No
uh,
problem.
Participant called Dr. Divya Velkula has asked, if we use
Okay.
potassium hydroxide as supporting electrode and silver chloride reference electrode, then what about junction potential, and how can we overcome during electrocatalysis of methanol?
Yes. This is one thing I keep on telling to people, whoever paper comes to me for peer review. We cannot use AGCL electrode in KOH because the electrolyte is clearly KOH, and the electrolyte that is in the AGCL electrode component, AGCL reference electrode component is KCl. Definitely, the transport number and the formal potential on OH minus and Cl minus are different, and they will be having different potential at the interfaces. So we are actually creating formal liquid junction potential at the interface of electrolyte and the electrolyte in the reference electrode compartment. So I would recommend you to go with HgHgO, which is a standard reference electrode for alkaline solution. And when you use HgHgO, you won't see any issues of forming liquid junction potential and the potential flaws in determining the standard potential of reference electrode. When you want to convert the potential of experimental potential that you determined in alkaline medium to the reversible hydrogen electrode. I keep on urging people that we should never use a reference electrode which is not having a common anion and common cation. So this is a kind of thumb rule you should always follow when you perform voltammetry. Not only voltammetry, when you perform any sort of electroanalytical technique, you must remember that the anions and cations in the electrolyte of the cell and in the compartment of the reference electrode must be the same and must be in the same concentration, which is also very important. Yes.
Okay. Thank you, sir. Thank you so much for answering all our questions. Thank you very
Thank
much.
you.
A small announcement to the participants. We'll be sharing our feedback link in the chat box in the Zoom as well as in the YouTube live streaming. You can just fill in your forms based on which your e-certificates will be generated. And now we have come to the end of the session. Uh, I would like to start this with a note that the most successful event is the one that achieves our goals and exceeds your expectation. With the hope that we have reached your goals and expectations, let's move on to the vote of thanks session. To begin with, I would like to thank our Madam Vice Chairman, Dr. K. Maragadamani, for giving us this platform to conduct this webinar. I owe my sincere thanks to our Secretary, Sir, Dr. S.P. Rajagopalan, and our Madam Principal, Dr. C.N. Ishwari, who have always been a great support to us in organizing this webinar. I wish to record my thanks to our guest speaker, Dr. Anantaraj, sir, for his exceptional and informative presentation. Thank you,
Thank you,
sir.
ma'am. Yeah,
And
I must also thank you for giving me this wonderful opportunity because everyone needs a platform to
yeah,
show who they are. Because I am very thankful to you. Thank you very
thank you,
much.
sir. Thank
Yeah,
you, sir.
yeah.
And also thank you for showing a keen interest in associating with us, sir. Thank you.
Yes, yeah. Thank you, madam. Yeah,
My special thanks to my dear friend and my well-wisher, Dr. Satyamurthy, for his encouragement and support throughout the organizing this event. I thank all my department colleagues who have put on a great effort and given me hand in hand in organizing this event. I also thank all my dear participants whose presence have made this webinar a successful one. Last but not the least, I would like to thank Almighty for all his blessings. Thank you, sir.
thank you.
Thank you, everyone. Thank you. Thank you, sir. Thank you for joining us.